And I'm Peter Roldan.
And today we're going to be discussing Marie Sophie Germain. She's kind of an underdog in math, but she became a world-renowned mathematician and a pioneer for women in mathematics specifically. So in the beginning, Marie Germain was born in Paris, France, April 1st, 1776. This was 13 years before the French Revolution, which is really important in her story. She was born to a wealthy family. Her parents were Anne Rose Francis and Marie Germain. So at the start of the French Revolution, at the age of 13, she was actually forced to stay inside for her safety and stay in hiding. So she began to read many books in her father's library connection in her spare time. In this time, she actually taught herself Latin and Greek. This way she could be able to read the works of mathematicians Isaac Newton and Leonard Euler, two very distinguished mathematicians in their field. So her introductions into mathematics was at the age of 13. The Bastille fell, marking the beginning of the French Revolution. This atmosphere at the time caused her to stay safe and hiding. Marie spent her time in a lot of solitude, and she was deeply inspired by Archimedes, a very famous Greek mathematician. His studies were in physics, engineering, and astronomy. This sparked her curiosity and her passion for a discipline in mathematics. His death specifically was the reason she began to teach herself math, and it was highly stigmatized for women at the time. Women were just expected to be wives, mothers, and homemakers. But that didn't stop her. Even though math was a subject that girls were encouraged not to learn, her parents even went as far as trying to stop her when they kind of caught on that she was self-teaching herself math. Her parents began to make her bedroom cold, anything they could do to sabotage her studies. They would even take away her candles at night so she couldn't read by candlelight. But all of these efforts really didn't stop her. If anything, she became more determined. She stole back those candles at night and she continued studying from there. So 5 years later, at the age of 18, the École Polytechnique was founded. This was an academy for teaching mathematics exclusively to men. She found a way to secretly gather lecture notes from the Polytechnique courses, and she began to study them. She was especially interested in the teachings of an Italian mathematician called Joseph Louis Lagrange. She was interested because Joseph had made significant contributions to number theory, a subject she was deeply interested in, and classical mechanics. She sent him a paper of analysis on number theory, and she used a pseudonym to disguise her true identity because it was discouraged for women to participate in the field. He received the analysis, and he immediately recognized the talent in her letter, and he asked to actually meet the student. To his surprise, upon meeting her, he was shocked it was a young woman. But because of her immense talent, he took her in as a mentee, and he agreed to become her mentor for the rest of her academic career. In 1804, she began corresponding back and forth with the German mathematician Karl Gauss on number theory, her interest specifically in mathematics. It wasn't until 1807, 3 years later, where he soon discovered that his pen pal this whole time for those 3 years was in fact a woman. Gauss personally guided Marie in her research from then on.
So I personally didn't study at night through candlelight, so I'm not going to be able to explain number theories like her. But for anybody who kind of just wants to take a look at it and see what his theory was, I'll leave that up there for a couple seconds. Yeah, you guys definitely got that right. Okay. All right, so her contribution to this, right? As Marie Germain admitted to Karl Gauss, her mentor, she was unable to establish the existence of an infinite number of auxiliary primes, even for a single prime exponent. Indeed, Germain's grand plan was doomed to failure, as it was later shown that for each odd prime p, there are only a finite number of auxiliary primes that satisfy the non-consecutive p power residual condition. Germain herself eventually proved in a letter to Adrien Legrand, that for p equals 3, the auxiliary primes 7 and 13 were the only ones that worked. Nevertheless, this was the first time anyone had devised a plan to prove Fermat's last theorem for infinitely many primes exponents, rather than on a case-by-case basis. So she kind of brought in a whole different approach to math that was rather unique, and don't even get it actually got her a lot of recognition from her peers. Unfortunately, she did not receive a degree from the school, so it's like you brought in this whole new approach to a problem that many people were like putting their heads into and trying to solve one by one, and she was like, you know what, let's go ahead and do this rather on a case-by-case scenario. Go ahead. All right, now for physics contribution, really there was a call for papers, which is really a test that was put out there. They had a problem they couldn't solve related to surface vibrations. Wave vibrations is tied to surface vibrations and is a subject that permeates almost all of physics. Marie never received a proper education and therefore would submit a paper filled with errors in her first attempt. She gradually learned from her peers and resubmitted it 3 times. Although she won under her own name and was the first woman to win an Academy of Science Prize, she could not attend the award ceremony or take part in academic sessions. This was because of the Academy's tradition of excluding women. Which is like, yo, dude, I just solved your whole problem and you're really not gonna let me get any recognition. This will kind of explain a little bit as to what her problem was.
In front of me is a giant metal square, and I'm going to use...
Oh, I'm sorry. Sorry.
In front of me is a giant metal square, and I'm going to use this as a kind of blank piece of graph paper to plot a random distribution of couscous. Okay, there we go. It's a scatter plot. Okay, there we go. Now, this is a pretty random distribution of couscous, but when I take my bow and I play this metal square like an instrument, this random distribution will suddenly become decidedly unrandom. Here we go. Okay, this is called a Chladni figure, and there are a few different Chladni figures that I'm able to make with this plate, and I'll show you a few more of those later on in the video. Chladni figures were discovered by someone called Ernst Chladni. But although he discovered that you could make these shapes, he wasn't able to work out the mathematics that describes why the couscous goes where it goes. In fact, he used sand, not couscous, but I found that couscous works a lot better. Uncooked. If you're going to try it so hard. The mathematics of where the couscous goes is actually a really hard problem. And most of the work in solving that problem was done by a mathematician called Sophie Germain. Sadly, she got almost no recognition while she was alive for her mathematical achievements.
Alright, so her contributions to that, I mean, like, that's a pretty tough problem to solve, as you guys can see, trying to find the mathematics as to why that occurs, and you could have different strokes, different vibrations that will cause different patterns. And she eventually ended up figuring it out. And despite having very little education, where she didn't know how to write papers, she didn't know how to probably communicate, but she always had the help of her mentors to get her through. And on the 3rd time, she actually was able to win the prize. She submitted it 2 other times, and it's like she had the right answer, but they'll like dismiss her because, hey, your spelling's off, or hey, you don't have this a certain way that we were supposed to do it. But she still pushed on through, and thanks to her push, we have a lot of impacts that she has had on our mathematical world. So she's helped a lot of other mathematicians still push on through. And as far as physical attributions, the Eiffel Tower, which we know requires a lot of physical engineering, a lot of her work was used to construct it. And it sucks because she doesn't get that recognition for that. So this is just a little quote of her understanding like her role. And I think as us students, we may not realize that someone had to put in so much more work before for us to continue to do the work we have today. Any questions?
What made you choose Sophie Germain?
I thought it was really important because this audience is relatively young to kind of showcase and emphasize that it's really important to be disruptive in places where you're not welcome. You can make a seat for yourself, you know, there's a seat for everyone at the table. And another thing, I kind of want to call back to what you've been trying to emphasize for this whole semester, is that collaboration is really important. As talented as Sophie was, she wouldn't have gotten as far as she would have if she hadn't reached out and collaborated with her peers. And I think younger students in college kind of have to learn this later on and the hard way, but if I could emphasize to all of you how important it is to build a community of other students who you can debate with, argue with, it's really important to learn how to go to areas where you're uncomfortable and lean into that. When you're, find a way to become comfortable with being uncomfortable, that's where you actually have growth. That's why they're called growing pains. If you're uncomfortable, it's a sign that you're on the right path and you should pursue it. It's not gonna really, you're not really gonna see any growth if you're just comfortable all the time. So you should really pursue things, even if it's your first attempt, second attempt, or third attempt on a subject. You can prevail if you just are consistent and courageous enough to take that on.
Yeah, and I personally I liked it because she had to try multiple times, and I know I'm one of the older people here, so I know this is like probably the start for a lot of you guys, taking just pre-calc, and then you guys got Calc 1, Calc 2, and you'll have things come up that are gonna stop you, or maybe like put you a bit behind, or you're gonna feel like I'm falling behind in classes, or I can't do this, but if you keep on pushing just like she did, you guys are eventually get through it.
And yeah, if you admire someone in something, just know that you already possess that quality. Otherwise, if it wasn't in you, you wouldn't be able to identify with it. So if you admire someone, it's a good sign that it's in you as well. You just have to nurture it and bring it out.
Any other questions?
Okay, so like, what has her field work in mathematics, do you guys know of something that we can relate to? Like, she did that, can you point out?
So that's, on her thing, it's numbers theory.
Mm-hmm.
So it'll be more, so I'm trying to put it into words without really butchering it up. Like infinity kind of type, as far as exponents. Yeah, so that's probably as much as simple as I can put it.
Like number theory, elasticity.
Yeah.
Like there's different applications for elasticity. So elasticity in physics is different from like elasticity in economics. But she contributed a lot to elasticity in physics. So how much force can you impact on a solid surface, you know, without it having to break? So that's something you could apply easily to like safety, you know, protocol of when you're constructing a building for earthquake resistance in California. You want to know like how much can this building withstand? That's, you need to know that. So yeah, bridges,
Makes
bridge
sense.
construction. Yeah. Yeah. Any other questions? No.
It's my fault. So she ended up dying in June 27, 1831. Unfortunately, she dies of breast cancer, and before they had actually submitted for her to get us a diploma, right, a degree. She died before that was possible. But at least you guys know about her now.
Great. You know, it's really interesting. When I took math classes, you know, when I was in college, we didn't ever study one female ever. We didn't know any females at all. They just were not part of the history. They weren't in the math history books at all. And I'm surprised at how many people choose to do things, to do reports on female mathematicians now. Because people wouldn't even dream of including them before. And even my professors, I only had one female and they wouldn't hire her full time.